Let's talk about some of the problems you might encounter when troubleshooting routing issues. We'll do this using a sample network with multiple internal subnets connected to the internet. The first problem we'll look at is one where a specific device can communicate with other devices within its own local subnet, but is unable to communicate with any other devices on any other subnet. Be aware that this may not actually be a routing problem at all. The first thing to check is the default gateway setting on each device. The default gateway identifies the router that is used for communications outside of the subnet. It's possible that the wrong default gateway address has been used on multiple computers. The most likely cause of this is a DHCP server that is assigning the wrong default gateway address to all hosts on the subnet. In this case, hosts will be able to communicate with each other, but would not be able to contact the default gateway router. If the default gateway address is correctly configured, then you can move on to troubleshooting the router itself. First, make sure that the router is actually connected to the network. You can use the route command on the router to view directly connected routes that have been set up. Make sure that this directly connected network is actually listed, which identifies that the router has a valid connection to this subnet. The next thing you look for are other entries that identify routes within your private network. For instance, if these devices cannot communicate with any other routers on the private network, the problem could be that this link is down. Or it could simply be that the router has not learned about these routes from the other routers. Using the route command to view the routing table helps you see at least what networks the router knows about. One possible issue that could cause this to happen could be problems with the Neighbor Discovery Protocol, or ND. ND enables routers on the same link to advertise their existence to neighboring routers and to learn about the existence of their neighbors. Routers use ND messages to identify the link layer addresses of neighboring devices that are directly connected to the router. ND allows routers to know when neighbors become unreachable or inoperative. To do this, it periodically sends and receives small hello packets to and from neighboring routers. If hello packets are not received from a particular router, ND will assume that the router is not functioning. Issues can occur when using a large subnet for point-to-point links between routers, particularly when using IPv6. By convention, we typically use a 64 prefix on each subnet when implementing IPv6, allowing for a very large number of hosts on the subnet. But a point-to-point link between routers only requires 2 hosts on the subnet, one on each router. As a result, it can take a very long time for ND to perform address resolution for all possible hosts on the link subnet. This aspect of ND is amplified when it tries to scan a subnet for connected hosts. Some denial of service attacks use this weakness to exploit routers using a flood of ND data. As a result, newly connected devices may not be recognized by the other routers they are connected to for a long period of time. As a recommended best practice, consider using a very small subnet on the point-to-point link between routers to reduce ND traffic. The recommendation is to use 127-bit prefixes on these links instead of the conventional 64-bit prefix. Let's look at another problem. Suppose a host can communicate with almost every other subnet, but it can't contact any device on one specific subnet. In this case, one of the first things you might do is check the routing table on the default gateway router and look for an entry for that problem network in the routing table. If an entry doesn't exist, then you can check the configuration of the routing protocol, or you can just statically add the route so that the router can properly route the information. If you still experience problems, you may need to check the routing table on every router in the path. Unfortunately, this may not actually be possible because you may not have access to these devices. If this is the case, check the path to the destination network using the traceroute command from the host. The traceroute command will show you the path that is used to reach that destination network. If there's a problem, the traceroute command may return a partial path. Then it will return an error saying that the destination network cannot be reached. Suppose, for instance, this router appears to be the point of failure in the path to the destination network. These other routers may have routes in their routing tables specifying that this is the path to route traffic. But this router may not have a valid connection, or it may not know about that destination network. The traceroute command will help isolate the problem. A broken route to a destination host could be caused by an MTU black hole. This condition is caused by black hole routers. A black hole router drops packets if the size of the packet exceeds the maximum transmission unit, or MTU size, it can support. We call it a black hole because the router does not send an error message to the sending host when it drops an oversized packet. In essence, the packet enters a network black hole. If you experience an unexplained broken router, you can use the ping command to try and locate the possible black hole router in the path by including the following parameters along with the IP address of the destination host you're attempting to reach. -F causes ping to send an ICMP echo packet that has the do not fragment bit set. -L sets the size of the ICMP echo packet. The results of the ping test using these options will provide you with several key pieces of information. If the MTU size supported by each router in the path is the same size as or larger than the MTU size of the packets being sent from your source system, then you will get successful ICMP responses from the destination host. If there are routers in the path that have been configured to a smaller maximum MTU size, but they return an appropriate ICMP destination unreachable packet, the ping utility will display an error message indicating packet needs to be fragmented but DF set. If there are routers in the path that have been configured to a smaller maximum MTU size, and they do not return an appropriate ICMP destination unreachable packet to the sending system, the ping utility displays request timed out message. The traceroute command can also be used to identify routing loops. A routing loop occurs when data is being passed back and forth between routers in the path instead of forwarding it to the destination network. For example, traceroute may show something like this. We'll use letters to designate destination networks. The path may go from network A to network B to network C to network D, and then you'll see a series of networks that appear to be repeated. In this case, the path B to C to D is repeated, forming a routing loop. The router at B passes it off to C, which goes to D, which passes it to B, and which goes back again to C and then to D. Drawn out this way is a better visual indication that the packets are just being looped throughout these routers. Routing loops almost always indicate a misconfigured router somewhere along the path. Either routes are not being shared correctly, or a router is not configured correctly. Here's one example of how a routing loop might form. Suppose you have a private network connected to the internet. This network has a web server that can be accessed through the internet. The ISP is configured to forward all traffic for that web server to a router at your private network. If this link is actually down, this known network will disappear from the routing table of this router. But this router may be configured with a default route, which is 0.0.0.0. It will receive a packet addressed to the website, but because this route no longer exists in its routing table, it will determine that it's an unknown destination and send that information this direction. The ISP router receives that packet addressed to the web server and again sends the packet this way. And then that process repeats itself. When you see a routing loop, you may need to just wait until the down connection is restored, if the router is not under your control. If the router is under your control, you should check the router configuration and the routing tables to resolve the problem. Other routing problems could cause hosts on your private network to be unable to access anything on the internet. In this case, you need to have an understanding of how your network connects to the internet. In most cases, your router is connected to another router at your ISP. So the problem with the connection to the internet could be with your router, or with the ISP's router, or with the ISP's interface into the internet. One of the first things to check would be the routing table on your router that connects you to the ISP. Use the route command and check to make sure that this entry for this network exists. That will tell you whether this link is up or not. If the link is down, you need to either troubleshoot your connection, or the ISP needs to troubleshoot the local loop into your business. Another thing to check for in the routing table is an entry for the default network. The link to your ISP may be up, but your router may not be configured to send unknown internet traffic to the internet. To address this, look for a route with a network address of 0.0.0 and a subnet mask of 0.0.0.0. Occasionally, you may find that the link is correct and the route is correct, but you still can't communicate on the internet. At this point, you could try pinging the interface of the router that connects you to the ISP. This may be the next top router that's recorded for this default route. If you ping it and you get a response, then you know that this connection to the ISP is valid. Another thing that may happen is that the ISP may have a web server or email servers on their network within their private network before it connects to the internet. You may find that you can communicate with these servers at your ISP and still not be able to communicate with anything on the internet. In this case, all you can do is contact your ISP, let them know the problems you're experiencing, and have them troubleshoot their link to the internet. And in most cases, they'll already be aware of the problem. A final situation related to routing involves remote access clients. For example, suppose a remote access client can connect to the remote access server but can't access any resources on the private network. In this case, we have a remote access client that connects to the remote access server. The remote access server is connected to the private network and allows access to the resources within the private network. If the remote access client can't establish a connection to the remote access server, you need to troubleshoot either the client or the server and figure out why that connection is not granted. If you can connect but can't access any resources on the private network, there are a few other things to check. The first thing to look for is the IP address that gets assigned to the client when the connection is made. When a connection is made, the remote access server, or a DHCP server, typically assigns the client an IP address appropriate for the private addressing scheme. For instance, suppose the client in this case is assigned an IP address of 10.1.0.15 using a 16-bit subnet mask. And let's say that the same subnet address is used on my private network. In this case, because the remote access client has the same subnet address as is used on the private network, the remote access client appears to be connected to the same physical media of the private network. However, it's actually separated by the remote access server on a different kind of connection. In this case, the remote access server should be providing a service called proxy ARP. With proxy ARP devices on the private network that need to contact the remote access client, such as servers that need to respond back to requests from the client, must know the MAC address associated with the IP address of the client. Because it's not actually on the same physical segment, and because modems don't have MAC addresses, the server acts as a proxy and builds a database mapping the MAC address associated with my interface to the IP address of all of my remote access clients. To make this process work, proxy ARP must be enabled on the interface that connects to the private network. Another issue you may encounter involves a remote access client that's given a different address on a different subnet from the private network. In this case, the remote access server is acting as a router. You need to verify that routing has been enabled so that packets from one subnet can pass to the other subnet. That's it for this lesson. In this lesson, we discussed troubleshooting routing issues. By properly identifying the symptoms of a problem, you can generally narrow down the source of most routing problems to a specific router or a specific link. In many cases, the problems you might find are not with routers under your control. Even if they are within your own network, you might not be in charge of maintaining those routers. By performing some simple diagnostic tests, you can narrow the scope of the problem and escalate the problem to the administrator who can best resolve the problem.